Okay, now that we have everything set up, we can make some adjustments to make sure that the experiment will work as well as it possibly can. First of all, we can try checking the alignment of the different components here, okay? We want to do this carefully because we know things are close to being all right, and we just want to make them a little bit better. So here's how we're going to do that. For each of these three components, the gate detector, transmit detector, and reflect detector, there are two adjustment screws on each of the couplers. One by one, we want to adjust each of these and try to maximize the signal. So I'll try it first on the reflect detector. There's a adjuster here, that's the vertical adjuster, and one over here, the horizontal adjuster. I'm going to start with the vertical adjuster, and I'll turn it maybe 10 or 20 degrees in the clockwise direction. Oh, the signal went down. That's bad. Let's go back. 10 degrees, 20 degrees. Oops. Need to restart the program here. There we are. 20 degrees, 30 degrees, a little bit higher, still higher. Oh, good. I made things better. I go a little further. I'm at a plateau. And then eventually the signal starts going back down. I'm going to tune back to the plateau, and it's maximized. Okay? That was one adjuster. And then I would do this with the horizontal adjuster here. Oh, I turned it, and then the signal went down. I'm going to go the other way. It goes back up. Oh, it's going down on the other side. I'll adjust it to be the optimum. It actually was already okay. And then I should go through and do that for each of these adjusters. The adjustments will probably be very small, but they might make a significant difference in the signal at the end. The last thing I'd like to do is this. You'll notice that the red trace and the white trace are not at the same level, but actually I expect that they should be. I expect, if everything is right, that photons have a 50-50 chance of being reflected or transmitted at the polarizing beam splitter. And so I should get the same signals. If that's not what's happening, it's probably because the polarization of the violet beam is not quite right when it enters the crystal. And so I'll make small adjustments by rotating the polarization rotator. So I'm going to try that now. I'm adjusting this component here and turn it one way, up. That made things worse. I'm going to turn it the other way. And you can see red goes up, white goes down. And then crossed, let me adjust it back. There we are. And now when I check the rotator, oh, it's actually now very close to 22.5 degrees. That's where it was supposed to be set in the beginning. We're all ready now to go ahead and do your measurement. I want to show you one or two other things before we stop. The only other thing I want to show you is this, really. Right now we're doing measurements where we measure for 1 second in each acquisition, okay? And then it shows us the result. In the lower part of the trace, you probably can't see it on the video, it's showing us the average of the last 10 acquisitions. That's nice, okay? So that data consists of 10-second averages. It shows both the average value and the standard error. You might well want to use a larger time, like do 10-second acquisitions and then show the average of 10 of these. That would be 100 seconds. That would be a nice measurement. If you want to do that, all you need to do is to enter 10 in the counting time. And now it will acquire data in 10-second increments. And then after it's done that 10 times, it'll show you an accurate average and standard error. You'll notice the count rates went way up because we're just counting for a longer time. Anyway, that's one way to do it, to collect more data to get more accurate statistics. You could do even larger numbers if you like, but perhaps this will be enough for what you want. Okay, good luck in the experiment, and we're going to stop our little tutorial now.